After creating the geometry in Creo, we need to import it into Ansys and start working on the finite element analysis part of the project. So before doing that, let's open this file, this activation of Ansys, and see what is in it. Here it says you have to open Ansys through the APDL product launcher, and also you have to choose the academic teaching license. So I'll do that. Here you'll find Ansys here, and scroll down until you find the product launcher, which is this one. Click on this. So here it is, teaching mechanical. You have two options. You better choose teaching. And for working directory, I'm gonna make another directory here called hanger. Okay, and choose that. Set bottom. And also the job name I filled previously, hanger, and I run. Also, I want to open this instruction. This is the whole instruction for your Ansys part. And in the beginning, you have the problem description and the same thing that we talked before. There's point A and point B. This part is fixed. The force is applied here, and the force is applied such a way that it passes through this A point. The value of P is this much Newton, and these are your elastic modulus and Poisson's ratio. So let's go down and see. These are your report requirements. And this is the part that we did in the previous video. We created a IGES file to be imported later with Ansys. And in this part, you have some commands to use in Unix in case you're using Linux, which I doubt. And here we start our instructions. The instruction starts here. So first thing is to import the solid model. So I will start this. By the way, when you start Ansys, in the beginning you will get some, not warning, some suggestions to participate in something, and I usually say no. Since it's not the first time I'm opening this, I don't see this, but you probably will see that. So file, import, IGES, OK, and browse. I'll go back to desktop, which I created the file. This was the file that I exported from Creo, the IGS, and open. And change this to from IGS file and OK. So here is our model. If you click on this part, you can move this with left click, you can rotate it with right click, and also zoom it with scroll. So first thing is to go to, let me check and be consistent with the instructions. Yes. So we start our analysis by defining an element type. Here in the preprocessor and element type, I add an element, add. It should be a solid element. This is a three-dimensional model, and we choose the 8-node model, 8-node element. OK. And in the options, we make it reduce integration. OK. Close. Next thing is to define a real constants. Add this one and let it be 1 and close. Next is material properties. And according to this, you have to go to, let me go up. In the material properties, it is material models, structural, linear, elastic, isotropic, and then you put these two numbers. And one thing you should notice is what we're doing here is that these software are kind of dimensionless. Previously in the Creo, we just put the numbers, and here we just put the number again. But we have in mind that our numbers in the Creo were in millimeters, and here we're working with newtons. So in the problem statement, you have 207 gigapascals, but what you need to put is 207,000 Newton per millimeter squared, which is equivalent to megapascals. So here is what I do. Material properties, material models, structural, linear, elastic, isotropic, and 207,000 and 0.3. Okay. And then next step is meshing. I collapse this, I expand this, mesh tool is global, and let's set the size 3. Okay. And it's tetrahedral, free, and I click on mesh. There's a warning, just ignore this. Pick all, close, and your whole model is meshed. Now the next part is applying the boundary condition, I believe. Yes, we did the meshing part here. And for boundary conditions, you just come down. First, if you did the whole thing the way I did in Creo, your x direction should be this way, y this way, and z would be perpendicular to this face. So in this case, your A will be here, the hole with the tag name A, and B is here. So here we need to fix this part. So we need to apply the boundary condition here, fix this hole, and apply our load here. To do this, I will come to the, usually I'll do it here, but in your instructions it says apply these loads in the solution part, so I do it according to the instructions. Here in the solution, you go to define loads, apply, structural, displacement on areas, and then I pick this let me zoom it here. Before I go here, I better zoom this thing. Let me bring it here, and you better do it as well. Now I click on areas, I pick this area, and there's another area at the bottom which creates the whole circle. I click on OK, I pick these two, and I want to constrain the whole degrees of freedom, so I choose all DOF, and you can leave this or put 0 here, and OK. So now you have fixed the displacement of this hole. Then the next part is to apply your loads, and your loads will be applied here. And let's go back to the problem statement. See, this is fixed, and this force, when you apply force in finite element softwares, you resolve your force in x, y, and z directions and apply them. Here it's just an arbitrary direction, and you can calculate the angle here and then calculate your x and y components of your force, but here in the instructions you already have those numbers. The numbers are, this is the whole number, and in x direction this is this, and in y direction it's this. And again, remember, if your x, y, z directions are the same as mine, you apply these numbers exactly. But if you had some mistake in your model creation, and for example your z direction is in this direction and y is coming out of this hanger, you have to put this number in pz, for example, if your z is in this direction. And one other thing to notice is, in reality, you would have a pin here, and the force would be applied to pin, and the pin has a contact with this inner surface of this hanger. So your force would be a distributed force on this hole. But here we are going to apply a concentrated force, which creates a stress concentration. To reduce this stress concentration, instead of just applying the concentrated force at just one node or one point, we divide it in half and put it in 2 points. For example, here I will choose a point around here and an equivalent point at the other side. So that's why this is your whole force. This is your force resolved in x and y, and these are divided in half, but we're going to apply these numbers on 2 points. So here is the same, apply structural force on nodes, and I will pick this node, and this node is somewhat equivalent to it at the other side. I click on OK. In x direction, what is the value? Remember, it's this number, 748.09, 748.09. Alright, and I'll do the same, pick these 2 points, and you don't need to hold shift or control to pick both, you just click on them. In y direction, it's 1613.07. Okay, and here this is our model. And now we solve this. So we are in the solution section. You go to solve, kernel S, and OK. And yes. And it is done. Since it was a linear analysis, it didn't take that long. Close this. Right now, to get the results of this analysis, you have to come to general post-process. And usually we come to plot results, contour plot, nodal solutions, and this is here, they are mentioned here. And then I go to stress and pick any of these. For example, one misses a stress, and it should show. For some reason it doesn't work this way, so to fix this I come here, data, and file options. I pick this, and this is, we are in hanger, and these are the result files. I click on open, okay, and then here in read results I click on first set, and now it should work. Now let's see what you're required to check. The first thing is to check the deform and undeformed shape. I mean, to bring it in your report. So you have to take a picture of it. To do that, here is your deform shape option, and to see both of them, it's here, and this ghost picture is your undeformed, and this blue one is your deformed. So this is one of the pictures that you need to put in your report. And then for the rest of them, probably all of them are in the null solutions, I think. One is stress and extraction, first principle stress, one is stress, and the rest are translation in X, translation in Z, and the sum of the translations. So in the null solution, this is your X component of stress. This is your first principle stress. This is the one with stress. And for displacements, here are the displacements. X component, and as you see, the object is fixed here, so the displacement here are almost zero. And this is Z component, and the Z, the whole thing is almost zero, except probably I chose these points probably were not completely symmetrical, and that's why we have some displacement in Z direction. Normally we shouldn't have, if everything is symmetrical. And again, for the last one, the vector sum is this. Okay, and this is your last thing that you need to show. And you better save this any moment that you think you have done something important. And other thing is, if you want to take picture of this, you have to come here. You have to come to plot controls, capture image, and here is a high quality image of your results. File, save as bitmap file, it doesn't matter. Let's say this is u sum. This was a picture of vector sum of displacement. So, and you have to do this for the rest of the results. Let's come down and check what we did. It was in this folder. Yes, here it is. I think you can also check the change the background of this. Let me do that as well. Here in the plot controls, probably you can change the background, create best quality, background. Let's see if we can make it. Oh, there are no white option. And right now I cannot find this. I haven't worked with this software for a long time. But you can search this and see if you can find an option to change the background. So actually you're not going to print this. You're going to make a PDF file of it, so it doesn't matter. And here you go. And the final part of your project is to solve this by hand and compare the results. Probably compare the maximum stress that you get, or moment. I'm not sure. Let's go up and see what is your final part. Yes, you need to provide the results of your analytical results for stress, which is basically you have to solve the moment for this hanger when you have this force, and then divide it by the cross section of this to get some stress. And you have to pick a point around here for the cross section, and you know what to do. And at the end, you have to compare the stress that you get and also the stresses that you have here. With, I think if you apply your force here, your stress would be about, it would be about z direction. So it is sigma y, I think. Anyhow, just notice one thing. If you go to one misses stress and click on OK, your maximum stress is here, and it's about this number. It's actually this number, not about. It depends on the point that you applied your force. And at the top, you have this value for your maximum allowable one misses stress. So based on this results, it cannot tolerate that force. So you have to do your analytical, get your analytical results and see what you get using those methods. Good luck.